very appreciated Professor Ye can let me come to the National University to do the presentation. So today my presentation is the application of NTR and MMR in outer space. And I am a high school student, first of all, and this is my first time to the vestibular lesson to do the PPT. So in this presentation, I will use the simplest words and the original to explain the NTR and MMR in outer space application. So first of all, I want to introduce the nuclear space. And you can see this paper. I have some presentation note in here, and there's additional content. So in early space race, it's almost 1967. The nuclear space was considered as the final weapon in spacecraft area to be developed, because the nuclear has the highest energy density among all of the fuel and the energy generation. Such that the nuclear space, we will wish it could provide the thermal, electricity, and the rocket engine power by the mission. And we need to use the nuclear reason is in outer space we have the solar plant to generate the energy, and we have the fuel cell using the fuel like hydrogen to generate the electricity or thermal. But in outer plant is sun, and this is is Earth. And in the outer of the Earth, the solar energy will gradually decrease because we are too far from the sun. So the solar energy will decrease. And the solar energy will be decreased, and the electricity power will decrease either. And such that we need to find other energy generator to generate the energy, to let the human the instrument to use. Therefore, United States and the Soviet Union start to develop the nuclear power in space, providing thermal and electricity, such that the US started to research the system for nuclear auxiliary power. And nowadays we call it project is SNAP project. So SNAP project has the NASA developed two types of nuclear power generator. One is CNR. This is SNAP A. I will introduce the MMR chapter, and CNR is the most likely the modern MMR design. They have a bit different. I introduced in chapter 2. So the other one, we have two types to develop it, and the first one is CNR, and the second is RTG, radioisotope thermoelectric generator. And RPG is actually using the decay energy to generate the power, and it can provide the electricity and the thermal. And you can see this is a very and this is the Voyager 1. Voyager 1 is a spacecraft, and it is searching to the outer planet. Yes, it's just that outer planet. And this one is RPG, and this is 3 RPG, and totally weight there's 3 generators, and this generator can provide almost 400 watts power electricity. And it is very tiny small to compare with the fuel cell or solar plant. So it is very tiny. And however, the RTG using the radioisotopic generator energy has a lot of advantages, like it is slight and very tiny, can be the middle level space mission energy provider, and it is very stable and the rate doesn't require any maintenance. And why it is very stable? Because the decay energy is not require any environment fabrics. And then you will see a movie. You may ever see. Just wait a second.
Which is why we did it. You're right. And planted that flag so we would never be stupid enough to accidentally go near it again. But as long as I don't break it.
This is RPG. It covers over the sand and it still works. And if you haven't seen, this is the market. It's very stable for the outer mission environment. And so, in an emergency, RTG could serve as the negative energy provider for all the planet or as a key source to keep the astronaut warm. However, although the RTG is very powerful and tiny and stable, it has a little kind of disadvantage. Although this radioisotope is very stable, the energy supply will gradually decrease because the radioisotope will half-life of. Wait a second. The RTG we usually using the plutonium-238 to be the fuel, and the plutonium-238 half-life is almost 90 years, and after 50 years, the power generation will gradually decrease like this photo, like this video. You can see in first year, it's a 100% power generation. And after 10 years, it's gradually decreased to 80%. And 30 years, it's almost 70%. It gradually decreased. Then, if you know the Voyager 1 need to close some component, experimental component to maintain its operation. And it is very this is a very critical problem that RPG need to solve. And RPG design scale is too small to apply in larger spacecraft. It is because RTG field, like the plutonium-238, you can see I have noticed in the paper. In page 3. In page 2. Because of the material production problem, only Tsung-Kuang refers site can produce all the mission and experimental needed radioisotope material. Especially plutonium-238 is very hard to produce. I remember this number because I got to be the energy supply. Otherwise, your project will be a problem, become an issue, become a problem. So you can see there's a forage 1 and 2 there, like, and power decreasing, materially decreasing, and such that the RTG will decrease its energy, and its working years is only 40 to 50 years, such that NASA starting to research the MMR. The MMR in outer space is actually we call the CNR. CNR before that is compact nuclear reactor. But they're mostly designed also the same. They are different in the heat exchanger and the coolant. This is a type of the SNAP project. This is called SNAP 10A. It's using highly enriched uranium as a fusion fuel, and the NAP allows it to be the coolant. And it transfers the heat to the thermoelectric converter. We call it TC, and it generates the electricity to the other component. And this is like a human height and healthiness is 400 kilograms. In page 3, you can see table 2. In CNR SNAP 10A weight is 431 kilograms. And to compare the other component, it is a little kind of heavy. It is a little kind of heavy, but its power generation is very large because the CNR and MMR mostly the advantage is it can change the fuel rods. So we can bring more fuel rod to the space, to the outer space, and in outer space we change the fuel rod to reach out the longer working years. And SNAP 10A cannot change the fuel rods. In recent years, we have a newer reactor called kilo power, and that one can change the fuel rods. The MMR and CNR approach is...
We need to go faster because we are running out of time.
Okay. Unlike RPG, SNAP 10A can store its own fuel for billions of years, 95% of uranium to certify, and because it is a reactor, so working years depending on how many fuel taken in a mission. And it has the highest power generation efficiency among all the generators. And SNAP 10A has a higher thermal energy co-generate compared with RPG. But SNAP 10A design is very fragile. Fragile is a word that is quite... this is because the reactor in the outer space, we cannot get any neutron source to use. So all of the CNR face a problem because in outer space, the spacecraft is hard to conserve the neutron source. So CNR actually never shut down. And after it starts up, it always it cannot shut down, or otherwise it cannot reopen. All of CNR design mainly different with MMR is CNR coolant is solid, and this is because in space we always using thermal electric converter after or steering engine or to generate the electricity. Component maintenance is more frequent than the RPG. And this is recent year we will test it in the Artemis mission or human go to Mars mission. This is called kilopower. And in page 5 and 6, I have they call it of introduce this kilopower, and because of the time limit, I have this one. We go to the NTP application. The NTP rocket engine, which uses the reactor to heat out the propellant and accelerate the rocket. The NTP full name is nuclear thermal propulsion. The first NTP application is in 1962. Early than that is called NER3A. NER3A research in Los Alamos National Laboratory and in 1972. Before the project ends, the NER3A has one of its experimental wet tests in Los Alamos National Laboratory. So NER3A is experimental engine. The NTP current is we using the hydrogen to be the coolant and the rocket engine fuel. And we're using the hydrogen. It is because the hydrogen is very compared to the oxygen. It's very easy to conserve in the outer space, and it has higher thermal efficiency than the oxygen, liquid oxygen, in use of NASA chemical rocket. Using the hydrogen as a component, the solid core design would typically directly specifically includes ISP, which is about twice more than the other liquid hydrogen with oxygen design. Oxidizing engine. The other chemical engine need to use the oxidizing engine to work, but the NTP doesn't need the oxidizing engine. So it can without any oxidizing engine to work, and it can bring more fuel than the chemical engine. And hydrogen is left at low pressure. It began to dissociate at about 1,450 K. This is the temperature. And at the high pressure, around 300, 3,000 K. This is lower than the mass of the solid, specifically increase the ISP. And NTP current is never mind. I didn't know where that was. NTP phase program was a lot. NASA and the DOE and Optimus program engineering recently was wondering about what to do when the reactor runs out of fuel. Began to say, I need to expand NTP working failure. Cooling past the reactor core and bring the heat out, but when the engine doesn't working, the reactor needs to find the other way to cool it because an SS exists. An SS is called non-shutdown system. It's to monitor the neutron flux to the reactor, and it will prevent the reactor shutdown by using the automatic electrical device. And to solve this problem, because we have an SS6 and it's working, so an SS we need to close first. And to solve this problem, reactor can design two currents: the open circuit and the closed circuit. In open circuit mode, the reactor can stay on higher power level because the liquid hydrogen can effectively cool down the core. In closed circuit mode, the reactor can insert the controller and make a neutron reflector in higher angle to release the neutron. The heat can transfer by TC component, and it's need to on the lower power level to make the TC component and working normally. In final, I want to introduce the NTP mostly difficult technology problem, the out of fuel. When the fuel was exhausted, the reactor needs to find the other way to cooling the reactor, or we need to find the other coolant to transfer the heat to TC. NASA and DOE designed two solutions: maintaining the minimum coolant volume that can maintain the reactor operation TC to to transfer the heat and make NTP become a CMR to generate energy. Last, I need to consider the power to the negative, otherwise the reactor must be motored down. To fully, and the second way is fully shut down the NTP. We can design the forward AC injection system and make reflector plate in highest angle to release the chain reaction, produce neutron, and finally shut down the NTP. And this is our discussing in the Idaho National Laboratory and the Lowest Livermore National Laboratory. And thank you for your attention. Thank you.
Okay, thank you. So, for NTP, hydrogen is the propellant. So, hydrogen is the propellant. So, how do you store the hydrogen?
Hydrogen, we use the hydrogen tank. In NASA, we will produce the chemical engine, and is using hydrogen to be a fuel. So it's not difficult technology need to solve. NASA execute the hydrogen tank to preserve the hydrogen. It's need to high pressure and the lowest temperature to store.
So it's not liquid hydrogen, it's
Liquid.
hydrogen get liquid hydrogen.
Liquid hydrogen. I have not had.
All right, thank you. Because of time, Arthur, you next. 对，收集了非常多的资料。